In this video, we're going to show that every differentiable function is also continuous. So the theorem is quite simple. It just tells me that if f is differentiable at a, then f is also continuous at a. And the proof, well, I pick f a differentiable function at a point a, then that means that the limit as x approaches a of f of x minus f of a over x minus a is L for some real number L, right? The limit exists and it's finite. I'm calling it L. So now what I'm going to do is to show that f is continuous at a, we need to show that the limit as x approaches a of f of x is equal to f of a, or the equivalent statement, that is that the limit as x approaches a of f of x minus f of a is equal to 0. And how can we use the condition that we get from the fact that f is differentiable at a to prove that that limit is indeed 0? Well, you see, if we multiply and divide f of x minus f of a by x minus a, we're going to get that f of x minus f of a is equal to f of x minus f of a over x minus a times x minus a, when x is different from a, but we're taking limits, so that's not a problem. And here, if you look at it, we have exactly the same quotient that we need for the definition of the derivative at a. So when we take limits, we know that the limit as x approaches a of f of x minus f of a over x minus a exists, is f prime of a. And well, the limit as x approaches a of x minus a is 0. So both limits exist. So I can use limit laws and say that the limit of the product is the product of the limits. So that is exactly what I'm going to do here. But then, as I said, the first one is the derivative, f prime of a, which we called it L in this case, and the other one is 0. So the limit is equal to 0, which is exactly what we wanted to prove. So here we have that indeed my function is continuous. Now, a big warning. The converse is not true. We're going to see in the next video that there are functions that are continuous but not differentiable.